Okay, everyone, radioactive decay is the next topic for discussion. Suppose you've got two chunks of some sort of radioactive substance. Okay, it's the same substance, and you put a Geiger counter to it. A Geiger counter is something which measures the electrons that are emitted from that substance. Every time an electron hits it, it gives a little click, and and you and you and you first of all notice that, say, this one is 1 pound and say this one is 3 pounds. Okay, and you put this Geiger counter to it, and you notice that in, say, I don't know, the course of a second, this one clicks 5 times. The question is, how much would you expect this one to click? And again, I hope that you answer 15, because if you have 3 times as much, that means you have 3 times as many atoms in there, and all those atoms have exactly the same probability of decaying. They decay just kind of on a whim, but how they decay doesn't depend on where it is. It doesn't depend on the pressure, on the temperature, or anything else. Everything we've seen about how things decay, it's constant over time, and it's constant no matter where in the whole universe it is. It's just one of those things that just kind of goes at its own merry pace, independent of anything out in the external world, because this is happening at a atomic level, at a nuclear level. Okay, and so the rest of the world is irrelevant to it. So the point is, if you have 3 times as much stuff there, you're going to get 3 times as many atoms that just decide to decay in that amount of time. And so what you're saying is that if Y is the amount of material which is decaying, then the rate of decay into a new substance from radium into lead, I believe, is proportional to how much is there. Okay, so notice that it's the same sort of equation that we had for population growth. The difference is that in this case, the amount of radium is going to be decreasing. The amount of lead is increasing, but the amount of the actual substance that you're looking at, the radioactive substance, it's decreasing. That means if it's decreasing, that means if a function is decreasing, here's t, and here's y right there. If it's decreasing, that means that the derivative is negative. And if the derivative is negative, that means one of these two things has to be negative. Well, y certainly isn't negative. That's the amount that's there. That can never be a negative number. That's always positive or zero. And so k has to be negative. So when you have radioactive decay, it's the same sort of equation we had before, but now instead of population increasing like this, it's going to, kind of like our contagious disease, it's going to decrease like that. It's going to be a radioactive decay. It's going to be an exponential decay like that. Okay, so that's what it's going to look like. So so that's basically it. So that's important to understand. Then I guess the other thing I just mentioned is that something that has been determined from experimentation is that carbon-14, which is a radioactive substance, its half-life of carbon-14 is how many years? 5,730 years. 5,730 years. Which is to say that if you have this amount of carbon-14, that after, here's your original amount right there. Let's just say it's, I don't care, let's say it's 8 pounds to start with. Then, after 5,740 years, half of it is gone. You're down to 4 pounds. And after another, if you multiply that by 2, what are you going to get? 5740 times 2 is 8, 14, 11,480 years, you're going to be down to half of that. So you're going to be down to 2. And then after another 5740 to that, 12, carry the 1, 5, 6, 7, 17,220 if I did it right, which would be that times 3. You're down to half of that, which would be 1. And then after another that, you're down to a half, and so on. So every 5,740 years, you're half as much as you were from when you started. If you start here after 5740, you're at half. If you start here after 5740, you're at half of that. It keeps decreasing exponentially. Okay, so that's the half-life. Okay, so that's what we know. So let's do the first problem, the first exercise here. It says, first of all, find the value of K, this value here, for carbon-14. Okay, that's the first thing we have to do. So let's let y is the amount, and let A equal initial amount. The initial amount. Okay? So what do we know? First of all, if we solve this differential equation, we've done it enough times now. I'm not going to keep doing it. We're going to get y is equal to, it's going to end up being A e to the kt, because your initial amount is when y is equal to 0. This is going to be e to the 0, which is 1. 1 times a is a. So there's your differential equation, which satisfies it. Okay, so we have that. So now that we have that, what do we know? We know that the half-life is 5730 years. So in other words, if t is equal to 5730, then how much will you have? You're going to have half of what you started with, right? So you're going to have half of A. So now we can solve that for K. Notice that the A's divide out, and I can take the ln of both sides. The ln of 1/2 is equal to, if I take the ln of this, I'm going to get the ln of e to anything is just going to be 5730 times K. And so that gives me that K is equal to negative ln of 2 divided by 5730. So see how I did that? How did I get that? The ln of 1/2 is the ln of 1 minus the ln of 2. And the ln of 1 is equal to 0. So it's just 0 minus the ln of 2. So that's one way of doing it. The other way of doing it is to say, oh, the 1/2 is the same as 2 to the negative 1 power. And then I can bring this negative 2 down front, and I get negative ln of 2. So either way, I like to write it like this because it emphasizes the fact that this is a negative number here. Okay, the ln of 1/2 is negative, but this really stresses the fact. Okay, so there's part A. So now let me, for sake of space, let me get rid of this, and I'm going to write it as A times E to the negative ln of 2 over 5730 all times T. So there's our equation. So that's number A. Or number 1, rather. Number 2, in recently dead material, a gram of carbon has enough C14 that a Geiger counter clicks 14 times. Okay? Suppose you find a gram of carbon from a buried spear handle and it clicks 5 times per minute. Okay? So the amount of carbon-14 in the atmosphere, we're assuming that it's constant over time. That's a big assumption. There's no reason to think that it's going to be exactly the same. There's no reason to think that it's going to be much different. And so that's an assumption that's made. It's made by looking at carbon-14 over as long as we've ever been doing it and asking what is it that causes carbon-14 to be made. And so you look at those and you make your assumptions, but it's still an assumption, okay? So all of this dating is all based on assumptions. And sometimes people say, oh, those assumptions are all wrong, and therefore we're going to throw out the entire thing. Well, unfortunately, in science, you have no choice but to start with some assumptions. And if you want to start by saying the world is totally different today than it was yesterday, and it'll be totally different tomorrow than it is today, then there's no reason to do any science in the first place, because your assumption is that anything you claim to be true today is all going to be different tomorrow. So you need to start with some sort of assumptions like that just in order to get anywhere. And it doesn't mean that you're totally proud and everything, that you know for sure that it's that way, but that's you have no choice. If you're going to try to make discoveries about the world, you need to make some assumptions like that. So anyway, here's what we're assuming then. As I say, we're assuming that the carbon-14 that's in the atmosphere and gets absorbed into plants and so on, that it's going to absorb it at such a rate that the present stuff that absorbs it, the amount that's there per gram, is going to make 14 clicks on a Geiger counter per what did I say? Per second? Per minute. Okay, 14 clicks per minute. Okay, so that's the new stuff. The stuff that you found buried, okay, that was absorbing it while it was living, but once it got buried, it stopped absorbing it. Okay, so it had all that carbon-14, which was clicking it at this rate, but now it's buried, and so it's not collecting, it's not getting all that stuff from the atmosphere anymore, so it's dying off. So if it were continuing to get all the new stuff from the atmosphere, it would keep doing it at this rate. But unfortunately, it's dead and it's been buried, and so now it's doing it at this rate because a whole bunch of it gave rise to radioactive decay. So in other words, the proportion. What's this question is? The question is, suppose what percentage of the original carbon-14 is then remaining? So the amount that was there originally was making it click at 14 times per minute, but now it's only clicking at 5 times per minute. So this is the proportion right here, which is remaining, because the number of clicks is proportional to how much is there. Okay, so there's the proportion that's remaining right there. Okay. So that's the proportion, or that's the percentage. If you multiply it by 100, it would be a percentage. Given that percentage is remaining, how old is the spear handle? Okay, so in other words, here's what we know. We started off with this amount. Here's the equation right here. And after this amount of time, we don't know what the time is, but it's been under the ground for this amount of time. This is how much is left. That's how much is left, because the amount of clicks is proportional to how much is there. So the question is, can we figure out what t is? And the answer is yes. Now it just becomes a math problem. So first of all, notice that the a's divide out. And I'm going to take the ln of both sides and get the ln of 5 over 14 is equal to the ln of e to anything is just that thing. So it's going to be the negative ln of 2 divided by 5730 all times t. And now I can multiply and divide, and I'm going to get t is equal to 5730 times the ln of 5 over 14 all divided by negative, I'll put the negative out front, the ln of 2. Okay, and notice that this is also going to be a negative number because 5 over 14 is less than 1, so the ln of it is negative. So that'll be negative, and so if I wanted to, in fact, let's just do it. I'm going to change from 5 to 14. I'm going to change that to 14 over 5. And that'll bring a negative out front, and then I'll just won't even have the negative to worry about. So that's 14 over 5. 14 over 5. What's 14 over 5? That's equal to 2 and 4/5, which is equal to 2.8. So that's an exact fraction right there. And so I'll write that as 2 and 2.8 right there. Okay? So let's actually figure it out. See what we get. So it's going to be 2.8. Take the ln of that. And then 5730 and multiply it by that. And then take the ln of 2 and divide it by that. And I get, I did that right, 8511.495. So I'll say 0.5. 8511.5. So it would be that many years old. Okay? That many years old. So so again, this is if you were to do this for a journal, you'd say, well, how let's say it's approximately 8,500 years old, and you'd be in the rough ballpark there. Okay, so that's the idea. Does that make sense? It does, because it takes 5,700 years to get half of it, and here we're at about a third of it. So it's going to be more than 5730 years. If you did 5730 times 2, then you'd have a fourth of it. So what did we say that was? 11,400 years. After 11,400 years, you'd have about a fourth of it, but we've got more than a fourth. So yeah, that's a reasonable answer, about 8,500 years. Okay, very good.